Yes, doctor.
Okay. So we will start to do problems on chapter 16. Just before I will introduce the main formulas for each type of operations we will use. So first, we will start with cutting operations. Okay. In case of metal cutting, we will rely on shear forces to produce the cutting effect. Okay. So the parameters that will be involved in sheet metal cutting are the clearance between the punch and die, the stock thickness, and the type of metal and its strength. And in addition, the length of the cut. So we will define all of these parameters before beginning by problems. So as you can see first in this figure, when you perform a shearing operation, you have a die, a punch. The die is the fixed part on which you put your work part. The punch is the moving tool which will cause cutting effect by creating shear in the plane of cut. So you have here the different phases of the operation. So first you do a certain clearance between die and punch, and you move it towards the work part. Then you will have a plastic deformation when you have contact between the punch and the work part. This will lead to penetration of the punch into your work part, leading to fracture at the end, which will lead to the cutting operation. So in order to calculate what should be the corresponding clearance to use in your operation, in your cutting operation, you need to know first what is the type of metal you are dealing with, because this will affect what is called the clearance allowance. So the clearance allowance is a property of the metal used. Another factor will be the thickness of your work part. Okay. So here you have a table that will give you, depending on the type of the metal, what will be the clearance allowance needed for the different sheet metal groups. Okay, so here we have these different groups. So for example, you have for aluminum alloys and tempers, you have a clearance of 0.045, while if you have cold rolled steel or half hard steel, etc., you will need a clearance allowance of 0.075. So in any problem, when you have a cutting operation, you should determine what is the material used to determine what is the clearance, and from the thickness of your stock, you will determine what will be the clearance, which is the clearance allowance AC times the thickness. Now, in general, the clearance C in shearing operation represents the distance between the punch and die, as shown in the figure. Now, typical clearances in conventional press working will range between 4% to 8% of the sheet metal thickness. And the effect of clearance is very important. And we should use the appropriate clearance, because if the clearance is too small, then the fracture lines will tend to pass each other, which will cause a double burnishing and large cutting forces. While if the clearance is too large, then the metal becomes pinched between the cutting edges and an excessive burr will result. So to understand this more, you can look at the figure here. So as you can see here in figure A, you have the case of small clearance. So when you have small clearance, as you can see, you will have excessive forces acting on your work part, which is not appropriate. On the other hand, if you have a very large clearance, more than required, then the cutting operation will not be optimal. And as you can see, you will have oversized work. Okay, so from here we should use a value of clearance calculated from the following formula, and the unit of clearance is equal to the unit of T, since the clearance allowance is without unit. Now we have we have several types of shearing operations. One of these are blanking and punching. Okay, now what is the difference between these two? So the setup for blanking and punching is the same. As you can see here, this is the setup. You have a die, you put the sheet stock on it, and the punch will lead to the formation of a hole in your sheet stock. Okay, now Sometimes in performing this operation, your final desired product is the blanked piece. This is called the blanked piece. It is the part that is cut from your operation. Then in this case, we say that it's a blanking operation because the final work part is the part we cut. On the other hand, in case you desire just to produce a hole in your work part, then it's a punching operation because your final desired product would be this one, which is a part with a hole. Okay, so when the operation is the same, just what will distinguish punching from blanking is what is the desired part. If the desired part is the one that we cut, then it's blanking operation. If the desired part is the one with the hole, then it is a punching operation. And the size of punch and die will depend on if you want the size of the work part. And if I have a blanking operation, the dimensions will be as follow. So as you can see here, the blanked piece size is determined by the die size. This is why when you have a blanking operation, we say that the size of the die is equal to the size of the final cut part. On the other hand, in case I have a punching operation, then the whole size will determine the size of the punch. Okay? So if I tell you it's a blanking operation, you start by saying the size of the work part is equal to the so here if you have a circular operation, so if you are producing cylinders or holes in a cylindrical form, then the blanking die diameter will be equal to the diameter of your desired cut part. On the other hand, the punch will be equal to diameter will be equal to dB, which is the die size, minus 2 times the clearance, because you should always ensure a clearance from all sides between punch and the die. So here, since the form is circular, then you should have clearance from the two sides. So the diameter of your punch will be equal to the diameter of your die minus 2c. And I repeat, this is for a blanking operation. On the other hand, if you desire just to do a hole in a certain sheet stock, then your final product will be the part that will remain after a part is removed. Then the remaining part will impose the size of the punch, because the whole size should be equal to the punch size. Okay, so if I'm doing a punching operation, then the whole diameter will impose the punch diameter. So then we say that in a punching operation, the hole will determine the size of the punch. And then for the die, in order to allow for the clearance, we should have that in case of production of a hole, the die diameter should be dh plus 2c. Okay, now in general when we have a blanking or punching operation, we don't have here straight sides. We do a certain angular clearance, which is the die opening will not have straight lines. It will have a certain inclined line in order to if you want to have a smoother operation. So it will not be straight like this. It will be a little bit inclined. So as you can see, to allow the smooth operation here. Okay. So this is about the punching and blanking operation. Now, any question on this? Now, concerning the estimation of the cutting forces required. So you know that to determine the capacity of your press, you need to determine what is the force needed to perform the operation, the cutting operation. And since here we are dealing with shear, then the force is calculated as the shear strength times the area of shear. Here the area of shear between the work part and the equipment is equal to the lateral area of the cutted part. Okay, so when we cut the part, The cut part lateral area will be determined by the thickness times, so this is the thickness, times the perimeter of the part to produce. Okay, so here, for example, if it's a cylinder, then the shear, this is the shear area, it is the lateral area of the cylinder, then it will be equal to the thickness times the perimeter of the cut part. So here it is, for example, L will be equal to pi times D. Okay, and in case you have any other geometry, you calculate the perimeter of the geometry times the thickness to obtain the shear area. And then the cutting force is determined as the strength, the shear strength times thickness times cut length. Okay, so now, in general, in case we don't know the value of the shear strength, they can give us the tensile strength, and from previous chapters, we know that we can relate both, so the shear strength can be estimated by 0.7 times the tensile strength. Okay, but just pay attention that in case they gave you the shear strength, no need you use it, because this is an approximation, and it will not give you 100% the actual shear strength. So in case you have shear strength, use it directly. In case you don't know it, you know only the tensile strength, then you use 0.7 times tensile strength to estimate the shear strength. Now, these equations are used for estimating the cutting force, assuming that the entire cut along the sheared edge length is made of the same at the same time. Now, in this case, the cutting force will be maximum. It is possible to reduce the maximum force by using an angled cutting edge on the punch and die as shown on the figure. This angle is called the shear angle, and it will spread the cut over time and reduces the force experienced at any one moment. However, the total energy required in the operation is the same, whether it is concentrated into a brief moment or distributed over a longer time period. What do they mean by this? So here, if you are performing a cutting operation, this force represents, if you want, the maximum force to apply at one time. And in case you are cutting the whole perimeter at one time, this will be the force you need. Okay, because here it depends on the angle of your shear angle. So in case you have an angle like this, then at one moment you will experience the whole perimeter to a force at the same time. On the other hand, if you have a certain shear angle, then the cut will be performed over a longer period of time, because you will, if you want, you will gradually do your cut. This will help you into reduction of the maximum force needed at one time. Okay, but at the end the total energy will be the same, because the cut energy is the same, but the time of operation will depend on the shear angle. So if you have a zero shear angle, then you will subject the whole perimeter to a cut at the same time. This will allow you to have a smaller time of operation. Okay. In general, when doing the design, we consider we do it on the critical case if we have a maximum force applied. So if we are applying the shear at the same time as the whole contact mass using this form. Okay. Any question on this? So this is the material, if you want, for the shearing operations. So now we will practice on them, and next time we will introduce the engineering analysis of bend. So in a first problem, a power shears is used to cut soft cold roll steel that is 3.2 millimeters thick. At what clearance should the shears be set to produce an optimum cut? So first here, it is a very simple question. So in general, and this will be a part of a big problem. So they give us the type of material. We have soft cold rolled steel, and we have the thickness. So we know that the clearance that should be used in a shearing operation is calculated from the allowance, the clearance allowance times the thickness of the work part. Okay, so here from the type of material we can go to the table and get the value of AC. So as you can see here, the type of material used is soft cold rolled steel. So it is here. So since we are using soft cold rolled steel, then it is 0.06. Pay attention, if they just say cold rolled steel, they don't say that it's a soft cold rolled steel, then it is a different clearance allowance. So you should have the name very, very accurate. Okay, so you should look at the details. It should be perfectly the same name. Okay, so here, knowing the value of the clearance allowance from the table and knowing the thickness of your stock, you can get the value of the clearance required for your operation. Okay, so this problem is just to know how to calculate the clearance. Now we move to another problem. A compound die is used to blank and punch a large washer out of 6061 ST aluminum alloy sheet stock of 3.2 millimeters thick. The outside diameter of the washer is 25 millimeters and the inside diameter is 12 millimeters. Determine the punch and die sizes for the blanking operation and the punching operation. So here, we desire to produce the following geometry. We want to produce a cylinder with a hole. Okay, so this is the final part design. The outer diameter of the cylinder is given, and also the hole diameter is given. So here, to make this part, we have several methods. We can first do a blanking operation. The blanking operation will give us what? Which part? When I do the blanking operation, what I will obtain?
The middle part.
The cylinder part. Okay, the big cylinder without a hole. Okay, so as a first step, I can perform the blanking operation. So if I do first blanking, the blanking operation will allow me to create a cylinder of diameter 25 millimeters. Okay, and then after obtaining my blank part, which is the full cylinder, I want to produce a hole in it. So to produce a hole in it, now I will use which type of operation? I will use then the punching operation. So after obtaining this part, I will do a, when I do after punching, I will obtain the hole desired. So the second step is to do punching, and I obtain in this case the hole. And the hole diameter will give me, will impose what? The whole diameter will impose in punching operation will impose which dimension? Yes, very good, the punch diameter. Okay, so first let us start by the blanking operation. We want to determine what are the punch and die sizes for the blanking operation. So we already have seen in the course material that in blanking operation, okay, the size of the part D of the work part, okay, is equal to D of the die. So here the diameter of the die should be, in blanking operation, should be 25 millimeter. On the other hand, in the blanking operation, the punch diameter will be equal to what? So once we determine the die diameter, the punch diameter will be equal to 25 minus 2 times the clearance. And to get the clearance required, it is like the previous problem. We know the type of material. It is 6061 ST aluminum alloy. and we know the thickness of the stock, so we can get the value of C. Okay, yeah, we will find together the value of C. So this is the name of our alloy. We go to the table. From the table, this is our 6061 ST aluminum. So it is also 0.06 for the allowance, clearance allowance. And multiplying by the thickness, we can get the value of C. Then after this, we can calculate for the blanking operation. We know that in blanking operation, the die diameter is imposed by the size of the final product. So it's 25 millimeter, which is the diameter of the outer cylinder. And then the punch diameter will be determined by dB minus 2C. So we got it after calculating C from the table. So now these are the dimensions for the blanking operation. On the other hand, for the punching operation, as we said, the punch size is determined by the hole, okay? And the hole to produce here is of diameter of 12 millimeters. So in the punching operation, this will be the diameter of the punch. On the other hand, for the die size, okay, we know that the die size is always larger than the punch size. So d of die will be equal to dp, which is 12 plus 2c, and the clearance is the same one calculated in the previous step. So it's 12 plus 2c. Then we can obtain the die diameter in the punching operation. Okay, so as you can see here you have the details of calculation for blanking and punching. So for punching die diameter, it is dh plus 2c, and the punch is equal to the size of the hole, which is 12 millimeters. Any question on this? Okay, so let us move to another problem. A blanking die must be designed to blank the part shown in the figure. So blanking and punching will not always produce circular parts. You can have different geometries, okay? So here, for example, we want to produce this part, okay? This is the geometry, the cross section of the geometry in a blanking operation. And we want to determine what should be the dimensions of the blanking punch and the die up. Okay? First, because it's a blanking operation, then to determine the die openings dimensions, it is the same as the blanked part. So this is the blanked part dimensions. So we know that in blanking operation, the dimensions for the blanked part are equal to the dimensions for the die. So these are the dimensions of the die. Now, for the punch, what should be the dimension? We know always that the punch is smaller than the die, okay? So we will draw what should be the geometry of the punch. Always, when we have a blanking operation, we should pay attention to ensure a certain clearance between the die and the punch. So here I should have clearance from all sides, okay? So here, if I verify to have, if I make sure to have the clearance between the sides, then I will draw now what should be the geometry of the punch. So I will be always away from the from sides with a certain value equal to the clearance. So I will do like a shift, and this shift is equal to the clearance value. And this will give me the red line which I am drawing represent the lines of the punch. Okay. Now, in order to determine the length of each side, okay, it's very simple. So here, for example, this length, as you can see in the figure, this length from here to here is 85 minus 2 times the clearance, because I have clearance from this side, so this is C, and I have clearance from this side, so in total this length will be 85 minus 2 times C. Now, concerning, for example, this part, the same. I have the total length here is 50. I subtract C from this side and C from this side, so it's 50 minus 2C. For this value, the same. So this length will be 25, also minus 2C. Now, for this part, who will tell me this length will be equal to what? This one. Yes, very good. It will remain equal to 25. Why? Because from here to here I have 25 minus C. But then I will add again C to be at a certain distance from this side. So minus C plus C is 0. So the length here will remain the same. It's 25. Okay? Now, for this part here, this part will be imposed. Yani once you impose these lengths, you will have this part imposed, and we can calculate its value because this value here is 85 minus 50. So this is 35. Then this part, as you can see, it's 35 plus C from this side plus C from this side. So this part will be 35 plus 2C. Now, due to symmetry, this part will be equal to this one, so it will remain 25. And also this part is equal to this one, it's 25 minus 2C. And this part is equal to this one, it's 50 minus 2C. So I will write here the different lengths. So these two, this one, and this one will be equal to 50 minus 2 times the clearance. We have that these two parts will be equal to 25 because this length will remain unchanged. You have these two parts will be equal to 25 minus 2C. And here, this length here, okay, this will be, this one is 35. This one is 35 because you can calculate it as 85 minus 2 times 25. So the length here, but no need to determine it. Why? Because once you impose here, if you know 85 and 25, 25, it's enough. No need to put this dimension on the figure. Okay. Anyway, I will just put it. So this length here will be 35 plus 2C. You can verify this also by doing that this length is, this is 85 minus 2C. You subtract from it 25 minus 2C 2 times, so you get 35 plus 2C. And finally, this one is 85 minus 2C. Any question on how we determine the different dimensions here? So let me check your questions. No, guys, no. Here we don't have the die and we want to do a hole inside. Here we have a work part. Okay, look, don't confuse between the two operations. Here the idea is at the end always, yes, it's true that always in an operation you will do like a hole. But here the final product is not to have a part with a hole. No, the final product is the blank part. Yani this part will be cut from the operation, and this is the final part you want to have. You can perform this operation instead of doing blanking. You can have this final product using punching. How? If you consider that you have, if you have this part and you subtract from it, you do a hole like this, then this will be a punching operation. But it's not the case here. You are not producing a hole in this way and getting your final part. No, what you are doing is you have a die and punch with this geometry. So the part